Let's do a little demo of data fitting for diode IV. Let's suppose that you are measuring your current. We're going to know what the parameters are here, and this is an Lavi VI that you may get access to if you want to practice yourself. So let's suppose that I decide that this particular cell has a series resistance of 75 milliohms. Maybe it has a 210⁻⁷ saturation current, and for now the short circuit current is 0, so this is just a diode in the dark. And just like you would be doing in the lab, you would be extracting data by sweeping the voltage and trying to get a good IV that you can then fit. And just like as you've done in the lab, you'll probably sweep back and forth to get more and more data, and it's up to you how often you would do this in the lab to get the best possible quality of measurement. Once you've done this and you're happy with this, you would grab your data and maybe put it onto Excel. So that's what I'm going to do here. I'm going to plot it onto Excel, and what you can see is now I have the same data that I had and generated in my IV measurement setup, and I have it now completely plotted in a linear scale as well as a semi-log scale. So now the question is, what is it that I can do now to extract the parameters to fit this curve? The equation that we would use is the equation that is here, which is basically expressing the voltage now as the dependent variable, and the current is now the independent variable. So we could then vary the current and calculate the voltage, and then fit the generated data to the measured data. So what I've done here is just basically copied this or translated this equation into Excel, and what I'm going to do is now just copy it all along. So I have it all the way up to here. So I'm going to plot, copy that. Now that we have all that data, since this is my dependent variable, now I need to change my dependent variable. So, my independent variable. So in this case is the current. So I'm just going to copy the current there, and we are ready to plot. So what you can see is this red curve corresponds to the data that I'm generating with this equation, and the dotted line, or the graph with the points, represents my experimental data. So first thing that you may want to do is organize your data a little bit. This may become useful in the future. Right now it's not as big of a deal if you don't have it organized, but what I'm going to do is I'm just going to grab all of my data, and I am just going to sort it. So I'm going to sort this from max to min, for example. So now it's nicely sorted, and again, this may be useful later when you want to filter your data and use less points that you've actually extracted. Okay, so let's continue. In this particular case, I know that this diode has an ideality factor of 1. If the diode had different ideality factor, then I'll simply have an n multiplying KT into Q, and we can see what happens if that were to be the case where n is not equal to 1. Okay, so in this particular case, I have n as a fitting variable, but because I know it's n equals 1, then I don't have to worry about it. But I have still two variables, or two parameters that I can change to make the red curve fit the data points. So the first thing we can do is realize that if my diode is giving me significantly higher current in my model compared to my measurement, that means that the saturation current that I am proposing is much smaller than the actual one. So let's pretend that we don't know what the saturation current is. So I'm going to say 20 minus 4. As you can see, things get a little bit closer, but not necessarily there yet. Let's say 1e minus 6. Things are getting much closer. And now I'm going to go 2e minus 8. And now I've gone past the point. So now I know 1e minus 7. And we're getting close. And at this point in the linear scale, it's actually difficult to tell how good our fit is. But when you look at the semi-log scale, you can clearly see that that red curve is not quite on top of our experimental data. So if I wanted to keep going, I would go and do 2e to minus 7 and then right on. Okay, now in the linear scale, it's very useful because now we can see if the series resistance is being fit properly, if we fit the series resistance properly. So once again, I see that my model data, the red curve, is steeper than my measured data, which means that the series resistance that I'm proposing is lower than it actually is. So I'm going to go to 0.1. Now you see I've gone past that, so now I'm going to go a little bit further back, and we have it just right on. Now, of course, this data, I already knew what it was because we started with that right here. However, this would represent pretty much what you would be doing in the lab. One last thing to check is, how do you know how good is your fit? Well, you can tell just looking at the curve, just by eye, if things are actually okay. But another way of looking at it is looking at the difference between the proposed fit and the actual measurement. So if you were to do that, you would take the difference between the two and then divide by what we think is the actual data, or the actual value, which is the measured value. And then you would just extend that throughout the whole set. Then you would add the whole set and add it all together. And what you would see is that you want to minimize that data or that value. So for example, if I wasn't quite there, and if I was at 1e minus 6, notice that my error is a little bit bigger than it was before. Now I'm going to go back to my fit. The last bit that I wanted to show you is what happens when the ideality factor is not 1. So the ideality factor is just simply a factor n that multiplies this equation. And so what you would see is that in a semi-log scale, this line would actually change its slope. And so if we were to do 2, for example, here, you can see that the slope of the fit is significantly shallower than the slope of our experimental data. So in practice, you may start with n equals 1, and if you see that the curve that you are proposing has a slope that is steeper than your actual data, then you would start changing n until you fit n, is, and the series resistance.